welcome to our Global Networking Forum session on innovative lunar lander technologies for sustainable exploration. My name is AC Charania. I am the Chief Technologist at NASA from Washington, D.C. and NASA headquarters. And I have an esteemed panel that represents a wide assortment of lunar lander experts and pioneers within the world. And I was very excited that we can host such a panel. And we're going to make it very conversational and hopefully not a lot of kind of PowerPoint kind of efforts, but here a good conversation of the innovations, the challenges that this group kind of has had in the various global endeavors for sustainable exploration. I do want to make the point that we will have, if we have time, we will take questions from the audience on Slido, and I believe you might show a QR code. So please note this QR code, and as we go forward, if we have time at the end, as I said, we will take questions from those in the audience. So with that, if we want to begin, so on the panel here today, I've got a whole assortment of innovators, and so I'll probably use everyone's first name as we talk to each other. And so we have Tim Crane from Intuitive Machines. We have Masaki Fujimoto from ISIS JAXA. We have Dan Hendrickson from Astrobotic. And we have our friend Veera from ISRO. And representing all the United States, India, and Japanese innovation in terms of lunar lander technologies. All right, next slide, hopefully. So there's, I'll just start and preface in terms of some opening thoughts for me as moderator. There's a lot of missions happening. This is a NASA slide, obviously, of the various missions, both human and robotic, that we have over the next several years. And this is not complete in terms of what all the world is doing. But I think it's a good representation of the interest within government agencies, commercial industry for both crew and cargo services, and the innovations that are happening in cislunar space. So the bottom line is there's a lot happening, a lot of innovation. And these are not just innovations using the same existing technologies. There are new deorbit descent landing sensors, new propulsion systems, new survive the night systems, new hopping systems, new imagery, new capabilities that all of these providers and developers are providing. So it gives you a sense of that. I will take actually time for a little commercial for myself. I'm hosting a lunar autonomy mobility pathfinder workshop in a few weeks in Las Vegas that's looking at autonomy throughout this ecosystem of surface mobility that these entities on stage are enabling. So just a short plug for me. And then finally, this picture, which is my last picture in the introduction, which shows you the accomplishments of the people on this panels. So these are real pictures. These are not PowerPoints or fake images. And I, in fact, would recommend to the IAC that I do this panel every year. And next year, I have a whole different set of innovators on the panel with me. But these are the innovators from this last year or so in terms of real hardware, real landings, real attempts at getting to the moon and to the lunar surface. Some successful, some more successful than others, some having challenges, some overcoming the challenges. And that's a great story of innovation. Sometimes that innovation works, sometimes that doesn't. Sometimes you overcome those challenges, sometimes you hotwire those kinds of programs to make it successful. And that kind of excites me in the world of innovation. So kind of with that, let's start the conversation, and we've got about 50 minutes left here. And maybe I'll start with Fujimoto-san. In terms of can you talk about the various technologies and the early missions for your Japanese spacecraft and lander that you leveraged in order to accomplish the missions? That's probably the question that I'll start with for all the panelists and go panelist by panelist. So.
Yeah, I'm from the Science Institute of the Japanese Space Agency, and this, I think it's an iconic picture, but it's from our mission, which landed on the moon successfully on 19th of January this year. It's a very small lander. We call it SLIM, Smart Lander for Investigating the Moon. So S is also not just only for smart, but also for small as well. So we really wanted to make our mission small and smart. But at the beginning, it started with a kind of collapse of a big mission concept we have had 20 years ago. We had a nice lunar orbiter by the name Kaguya, and everyone thought that, oh, next step is the lunar landing. And everybody got together, and then the mission got beefier, and then it collapsed. But out of that ash, there were two guys who thought that pinpoint landing on the surface of the moon must be demonstrated. So those guys with I think had the motivation in the correct shape, kept on working for 15 years, and they came up with a big success. So it's the pinpoint landing by optical navigation that this small mission demonstrated. But because it's such a small mission, you only have limited resources. So how do you put all the algorithm into the limited resources available on this small lander? That really was the key challenge that the team members faced, but they managed it. What I mean by is that you really have to do all the processing very quickly. So how do you do that with limited resources? So they have to come up with again, smart algorithm to do so, and they did. And we ended up with this safe landing on the moon. By the way, it looks to be in a very acrobatic orientation on the surface of the moon. This is not something we planned. There was something wrong that happened at the last 40 seconds of the mission. But the pinpoint landing technology was already demonstrated at 50 meters above the surface. So this final 40 seconds is like giving us the charm to the mission and giving us even more motivation to the next mission.
Thank you. Going next to Tim from Intuitive Machines, on your first generation of landers, kind of the biggest technical challenges you had?
The key difference between a lander and just a spacecraft or a satellite is the amount of high impulse thrust you have to manage. And so really the whole lander system is built around managing propulsion from our perspective. And we had 4 things that we couldn't test until we got into orbit. We couldn't test the exact performance of the engine in a vacuum. We'd approximated it with a number of tests terrestrially. We had simulation and modeling. We couldn't test the free vehicle control of a large single engine gimbaled spacecraft. So we didn't have multiple engines. We're steering with a 2-axis gimbal. You can't free fly that in 1G. So we had to wait until we got into our first engine burn to confirm that our algorithms actually worked on an actual vehicle without lockdowns. Radios at lunar distance. So we tested the radios, but it's all simulated delays and attenuation. How are we actually going to perform 380,000, 400,000 kilometers away? And finally, our sensor interaction with the lunar surface. So we did camera modeling, we did camera testing with perfectly white images as much as we could, but the actual photons from the sun reflecting off the moon, hitting our cameras, the actual photons from our lasers hitting the moon and coming back, those are things that we tried to bracket. So the challenge for us was getting the risk mixture right, where we felt like we had done enough terrestrial testing that these systems would perform, and then demonstrating them orbit for the first time. And fortunately, we were able to check the boxes off on those, but it was something that we spent a considerable amount of time looking at. How do you go from the successes of other programs, how do you go from the historical achievements and demonstrated approaches to landing on the moon, and implement your new specific system and get enough testing that the residual risk on orbit is something you can accommodate. That was the big risk for us, the big challenge.
Our friend Vera from ISRO, in terms of the similar question for your incredible mission that had multiple components, some of the biggest technical challenges.
Thank you for the opportunity. As you know, the fundamental difference from the orbiting mission to the landing mission is it demands for new technologies and new systems. So one of the system is the sensors, which gives position and velocity information. In the absence of GPS in the moon, we have to use a terrain relative navigation sensors. So we developed a set of sensors which gives position information. We had altimeters, which works on radio wave frequency and laser-based principle. And also we had a velocity measurement in all the 3 directions. We had a new sensor called laser Doppler velocimeter. And also, towards the end, we have to avoid the obstacles, for which we used LANDA hazard detection and avoidance sensor, which is a camera-based sensor, where we took a picture prior to the landing, and we are stored on onboard. And just before the landing, we took a picture and compared with the onboard image, and by which we were avoiding the obstacle. That was one of the intelligence built in. And the second technology is the propulsion system, where we require a throttling engine. And we used multiple engines with 800 Newton capacity. And the throttling range is from 800 Newton to 400 Newton. And this is required during hovering stage and various stages of deceleration. So we developed a new technology with the throttleable capacity. And also we require a landing leg technology, landing gear mechanism, where we have honeycomb-based dampers, because we have to, at the time of touchdown, it has to offer the stability as well as it has to give a necessary strength. So we designed different touchdown conditions, like it can tolerate up to maximum of 3 meters per second in the vertical direction and 1 meter per second in the horizontal direction, and it can tolerate a slope of 12 degrees. And also, we do not know the terrain conditions, whether it is hard or soft. So according to that, we have developed multiple technologies. And also the mission design itself, as we were to utilize our own launch vehicle, which has a limited payload capability. So we have designed the lander of about 1.75 tons. And this lander has been carried by propulsion module, which will be taking the lander all the way to the moon, and where the launch vehicle is injected. And the launch vehicle has a capability of injecting approximately 4 tons of mass in GTO. From GTO, we have to go to the moon, and we designed a trajectory from GTO to the moon orbit, and finally, we had a set of deboost maneuvers, and then finally landing. And the landing itself, we designed multiple design trajectories, particularly on the algorithms, navigation, guidance, and control algorithms. And that also is a very new technology. And finally, upon landing, the tiny rover has to come out, and that also is a challenge, because we have to have a necessary orientation which has to look at the sun upon landing. And we have designed the entire lander for 1 lunar day, which means the precise landing and the orbit, the orientation of the lander has to be very precise, so that the rover comes out of the lander with the necessary systems are in place. So these are all the multiple challenges we had. And moreover, to qualify these systems, we had multiple simulation test beds, which captures all these failure modes. And to substantiate that, we have to conduct a necessary test. That is one of its unique tests, where we have to do at outdoor, like integrated cold test, wherein all the sensors have been characterized thoroughly for the dynamic conditions with the required altitude, with the required velocity, and also the propulsion system in loop with the navigation, guidance, and control. That is another challenge. We have to really see the closed loop is working. And also, finally, we have to qualify the lander legs. So we developed something like a Lunar simulant test bed for characterizing the stability conditions. So these were the challenges, I would say. And finally, we succeeded. Thank you so much.
All right, that's always a great story. So now, Dan, you've had some interesting experiences in that first mission and lessons learned. So I'd be curious on some of those technical challenges. I know you all have various follow-on missions as well, but I think I'm interested in your thoughts as well on this.
Yeah, thanks, AC, and thanks for the opportunity to be here today. In Astrobotics' case, we had a really significant anomaly that occurred in flight. We unfortunately had a valve failure that proved to be the most challenging technical issue that we had in the entire mission, for obvious reasons, in that we had a rush of helium coming from the pressurant tank that entered the oxidizer tank and caused a rupture. It was at that point we recognized it was not going to be possible to do the power descent because we wouldn't have the proper pressure. But we quickly pivoted the mission and focused on a few things. One was to get as much payload data for the customers as possible. In fact, 3 of the instruments ended up getting publishable science. So bittersweet result. We're really glad that still occurred. But then we also focused on getting as much data from the technical systems and the subsystems, to diagnose the valve issue, to understand what we needed to change for future missions, but also to prove out the rest of the subsystems on the vehicle. It's a little funny to say, but everything else on the vehicle worked as planned. land. So that kind of goes back to that point that I think you were making, Tim, in that you kind of have to make choices of what risk tolerance you're willing to take on particular subsystems. And one of the things that we're really excited about in this new era is that there's the opportunity to finally iterate. So now we're going to go back and we're going to add a pressure regulator in front of the valve that failed. We're going to add another valve after. We're of course also going to make a mechanical design change to the original valve. All those things allow us to make changes to assess where the weak point was. And again, everything else worked as planned, so we feel very confident about moving forward, and we've got an opportunity to, again, understand where the weak points are, iterate, and then fly again, ultimately.
All right, thanks, Dan. Maybe I'll come back on this side to Masaki-san for the next question. So we've had a good conversation from all of the panelists on these missions that you see here before you. Now I want to go a little bit to the midterm and farther term as we go forward in the conversation. So as you look, all of you, I'm sure, had interesting experiences, successes, lessons learned, and you're going to build more landers, hopefully, all of you on stage. So as you look forward to those later generation of landers, what are some technology gaps or shortfalls, as we call them, that you're thinking we have to solve these challenges and shortfalls for the future generation of landers? So maybe Masaki-san.
Again, might want to talk about this SLIM mission again. So we had two primary objectives. One is to demonstrate the pinpoint landing technology, which has been successful, but the other one is to demonstrate the two-stage landing scheme, which should be useful to land. If the terrain is rough or has a slope, we should be able to land on that spot safely. That was supposed to be demonstrated, but we could not because of this last 40-second trouble we have had. But what I want to tell you is that pinpoint landing technology and two-stage landing scheme, that should come in on combination, because if you tell your customer that you have the pinpoint landing technology, then the customer tell you, can I land here? And if there's a slope, and then we're gonna have to tell them, if you don't have maybe if you don't have the two-stage landing scheme, you're gonna have to tell the customer, I can navigate you there, but I cannot land on the surface, which is almost like a scam, right? So we wanted to demonstrate the combination of the two technology, which we think it's the smart way of performing a small missions, but we could not. So yeah, so what's the next occasions for us to demonstrate the two-stage landing? Oh, by the way, two-stage landing is as you can tell, our lander doesn't have legs. So instead of legs, we do have five, something like a sponge, you know. And then contact with the surface will happen only with one of them, and then you change the orientation of the spacecraft, and you contact the surface as if you're clinching onto the surface. That's the way I mean by two-stage landing and safe landing, whatever, even if you have a slope on the point you want to land. But we haven't demonstrated yet. So what's the next occasion? That's something is in my head now. Yeah.
Very good. Tim, next question to you. I know we've contracted at NASA with you for a few missions. So as you think about these later missions and even your roadmap, what are you looking at in terms of tech shortfalls?
Well, you know, one of I think the common themes you'll see of all four landers, and by the way, how cool is it to have four landers on one screen that have all landed or attempted to land in the last year? It's really, really exciting times. You know, all of these landers are very lean. They're small landers, really set up to demonstrate the core technologies in a lot of cases. Small amounts of payload. What that means is once we land, we're going to get operations through the lunar day. And then when the sun sets below the horizon, our systems are going to freeze, and then that was it. And so we kind of have this one-shot mission at this scale of lander. But as we begin, really as a cohort of organizations building landers, to move to the next generation, and now you're talking about landers with 500, 1,000, 1,500 kilogram capacity, we have an opportunity to begin looking towards survive the night. And now, these become assets and part of a lunar infrastructure to provide communication nodes, to provide navigation resources, to be literally a power and warming station for other vehicles, but for us to have use of these systems over and over. And right now, all of our first generation landers are kind of one shot for a lunar day, and we really need to take the step as we perfect these technologies, and it'll take a few more flights. I mean, the moon's a tough challenge, but I think that will be where we really see the same way we've seen reusable boosters change the launch game. Persistent assets on the moon really put us on the path to sustainability where we can build up infrastructure.
Vera from ISRO, as you're looking at future landers as well, what are the biggest technology gaps, shortfalls you're trying to address? Yeah, and I know you've even got joint missions with JAXA as well. So yeah, curious.
Yeah, we have a series of missions post Chandrayaan 3. The next mission is sample return mission. So it calls for different kinds of technology. We have to come back with the sample back safely to Earth. So it calls for docking in space and then escaping from moon, and then also we have to cross through the atmosphere. So we require a re-entry vehicle. There are a lot of challenges. And also for the future, the gaps, I would say, is long-term survivability. Right now, our missions are having one lunar day because we are heavily depending on the solar power. So we should have some mechanisms. Either the systems has to be qualified for a very low temperature working conditions, because we are also planning to explore permanently shadowed regions. That are the science aspects we are looking forward. So for which we require either nuclear resources, or we need to see that any other mechanism is available to have a long-term survivability. This is going to be the key. And also some of the asserts are required for the relay communication and navigation purpose to have a precise landing. And also now the trend is going towards the pole. And there the sun elevation angle is very, very low. And we are using visible sensors, and these algorithms, how it is going to work, and how the terrain conditions are going to be looked at. These are all challenges ahead of us, and we have to qualify those sensors with the different integration times. So these are all the big challenges we have.
Same question to you, Dan, but you can't use the answer of survive the lunar night. We've already heard that one. So give me some other challenges.
Because I was actually going to echo that, but I'll maybe take a different approach. I think there's going to be some unique tech challenges that will come from needing to go to the same location over and over again. I think it's great that we're going to have landers capable of going to multiple locations, because there's a lot of science to be done, and you can't necessarily go to the same place every time to do it. But with that said, I think a lot of folks are really focusing on going to the South Pole. And so, yes, you need to survive the night. We're big fans of things like micro power grids to help make that happen. But you're also probably going to need things like landing pads, because you can't have the abrasion of every lander coming down over and over again in a limited area. And when you combine that with things like potentially even beacons for the ability to actually do maybe TRN-less, so non-terrain relative navigation down to the surface with beacons that already exist, those are things that I think are well within our capability to develop, but they're not ready yet. So we need to work on those technology shortfalls so that we can go and do all of this sustained presence that we're looking to do, particularly at the South Pole.
Thanks. And now the next question, I think, goes to the theme of the IAC this year in terms of sustainable exploration. So I prepared the panelists with this question, so it shouldn't be a surprise. So, and specifically, let's talk about sustainable exploration. We can talk about it in the abstract, in theory, but you all are at the tip of the spear, as one would say, in real exploration, as we see in these pictures, of people who are actively exploring the moon. And as you think about it, how do you think about exploring the moon in a sustainable fashion, to the theme of this year's IAC? So this is maybe less of it could be a technology question, but maybe a broader question, as you are innovators and not just talking about sustainable lunar exploration, but actually exploring the moon and thinking about it. So maybe Masaki-san.
Yes, I'm a Deputy Director General of the Science Institute within the Japanese Space Agency, but I also belong to the Japanese Space Agency, which is in charge of the big pressurized rover to be deployed on the surface of Mars, of the moon. So we get to be invited to participate in the conversation, because science is always the central topic for even for such a big asset. But on the other hand, at my institute, we work on smaller missions, smarter missions. So how do you define the constellation? Variety of landers or rovers, so that that will enable more and more people to join and play a meaningful role in the exploration of the moon. That it's not just a slogan to me. That's something real, because I know both elements. You know, when I wear my space agency hat, I do talk about big pressurized rover, but in my institute with my colleagues, I talk about how to make our smaller missions even more smarter. So yeah, it's this. How do you define the nice? Maybe it's the architecture discussion, but how do you define the way of inviting more people in and let each size of the missions to play meaningful role while the humanity explore the moon? I think that's a nice topic to talk about. Yeah.
I think, just taking an aside, I think in the United States, from my perspective, we have both the CLIPS program, the Commercial Lunar Payload Services, and you see two of our providers here. We also have the Human Landing System program, and I like both, and I think both are synergistic with each other. To your point, we have big programs, but we have smaller programs as well that hopefully are growing as well, and both can work together. So, Tim, kind of same question on sustainability, and what's your thoughts there?
Well, not from a technological point of view, but from a planning and philosophical point of view, moving from a single encapsulated mission mindset to a campaign mindset, where you might say, okay, on this mission, we're going to land and we're going to deploy, and we have some very important science things and some demonstration things we're going to do. But I'm also taking something that's going to be put in place for a subsequent mission to come and then utilize that as part of what it's doing. And now you look across an architecture and it changes your perspective. We've begun working on our lunar terrain vehicle, which has a trailer attachment. So we think, well, I have one LTV, but what if I had many trailers with different power, communication, science packages on different trailers that are delivered at different times? And when we begin working and even working across organizations and saying, well, I've got this mission where I'm taking Article A, and then I have Article B that's going to this next mission, but I'm missing something else. Might we call a competitor up and go, hey, I know you've got room on your manifest, or call up other space programs and say, look, we're moving across multiple missions to do something sustainable, maintainable, but beginning to think about that architecturally and in a campaign sense, where we'll say, okay, I will do some things that build up as we go, and we're not in an encapsulated single mission mindset. And just things like building landing pads, because you're going to build up on that. And how cool will it be to go from being observers to builders on another celestial body? That's going to be a monumental moment, I think, that'll lead to that sustainability.
Observers to builders. Okay, that's good, interesting quote. Vera, your thoughts on sustainability?
Yeah, I would say the infrastructure requirement around the moon as well as on the surface is also crucial for the sustainability. Like, for example, how we have a space station around the Earth, we should have some kind of a gateway. Anyway, Artemis program is having, and we should have even our ISRO is planning such plans beyond the crew landing onto the moon. So we should have our own architecture, or we have to have a joint venture so that there will be a shuttle between the Earth to the moon, as well as from the moon to the surface. We should have another re-shuttle, so for which new technologies are required for cargo as well as a crew transfer, as well as to create a lunar station for a constant human presence on the surface. We have to see that how we have to utilize the regolith or soil to construct and develop an infrastructure. This requires different kind of an instruments. Like, lot of study is set to take place for a constant human presence, and also the infrastructure required for a relay satellite and communication, relay communication and navigation. Even though for Chandrayaan-3 we utilized different DSN network apart from IDSN from ISRO, we have utilized JPL 3 stations and ESA 2 stations, but still we were having a visibility gap. So in order to maximize the payload operations, this is also very crucial. So now the Moonlight program is there, and we too have our own, we are thinking of having some more relay satellite communications with the highly elliptical frozen orbit with the 2 inclinations. So such things are required around the moon as well as on the moon.
Dan, your thoughts on sustainable lunar exploration?
Yeah, thanks. I love the mention of Moonlight in the sense that it speaks to, I think, a sense of sustainability where folks are specializing. The idea that we're all going to build landers forever and everybody's going to be doing delivery missions. I think if we look back, 15 years from now, and if that's still happening, I think we probably failed in the sustainability department because cost matters. It's really expensive, as it's been pointed out on this panel, to just keep doing singular missions one at a time. So, in our case, we want to focus, we're going to continue to focus on delivery, but we really are excited about providing power through LunaGrid. And in that case, we feel like that's an opportunity then for other space agencies, for other companies to make use of power that's already there and then not have to bring the power solution with them every time for a HAB, for an LTV, for a science package. And so if you have, I think, specialization, that's one of the hallmarks that you've got the beginnings of something that's truly sustainable because it's going to bring down cost. And it's also going to invite other players to the table. They can see a role for themselves that might be a little bit different instead of a really high capital intensive activity like building a lander and buying a launch vehicle.
Thanks. Now, I think last question before we maybe go to the audience, and I will ask all of our panelists to take off their agency institute hats right now, and just as humans and smart individuals with me on the stage. Let us travel through time. It is now the year 2040. We are many years from here and many IACs from now, and who knows when we'll meet again in 2040. So I'm with you at the 2040 IAC, with all of you again. Give us your impression of what the moon looks like in 2040. All this activity that we've heard, from landers to infrastructure to cislunar space assets. What does the moon look like to you? And what is the vision of what a 2040 lunar surface kind of image in your mind that we can aspire to or get to? So Masaki-san.
Yeah, so I don't know how you guys came to this venue, but if you go outside of this building, there's a nice big green area where people are walking their dogs. So in 2040, on the surface of the moon, I hope the same is happening, but not the dogs. Astronauts walking their small rovers around it and exploring the environment in a very creative way. It's like what geologists do on Earth, not just following the instruction that's been prefixed, but the exploration has to do it in a more creative way. And maybe the swarm of small rovers may provide the tools to enable such a creative exploration. That's what yeah. So once you go outside this building, watch for dogs. And yeah.
Tim, 2040, what does it look like?
Well, the lunar orbit crosses the Earth's equatorial plane. We have the alignment of the nodes twice a month. And I think what you'll see spacecraft on their way on every ascending and descending node. And so in the same way we've become used to seeing regular launches into low Earth orbit, you will see the launch window opportunities to the moon with a regular cadence of launches every month, twice a month, 3 times a month. Returning vehicles are going to be bringing samples, materials, manufactured goods back from the moon in small quantities. And we'll have not only ISRU, but we'll have built habitats from lunar material at that time. And so by 2040, it won't be just the beginning of human habitation on the moon. The first lessons learned from human habitation on the moon, I think, will already start coming in, and we're going to be making refinements in that system. So it's going to be a very exciting time, and we're getting to the point where we can perfect the basics of transportation and communication and power management. What we as humans collectively do, the opportunity for cooperation there on a very vibrant Earth to moon and back and forth again transportation model. It's going to be exciting to watch.
So we may have a launch of a lunar lander at the beginning of IAC in 2040 and a landing at the end of IAC. In
That's right.
Is that true? Okay, all right. Vera, 2040, what does it look like to you?
Yeah, ISRO has put a target by 2040. We have to have Indian astronaut on the moon. That's what our target is. Before that, we will have a series of missions, both for science point of view as well as from ISRU point of view, and a lot of technologies we need to develop before the crew landing. And also, with respect to the previous question, lot of activities will be taking place on the surface as well as around the moon, and a lot of transportation reshuttles will be happening between the Earth and Moon, and we can see a lot of activities. That's what I can visualize now. Thank you.
Dan, 2040.
So I think by 2040, we will have demonstrated it's possible to extract a resource, and the first entities that are not space agencies will be pursuing actually closing the economic case to do it, having seen the demonstration and starting to gear up for a major investment and looking at doing that for the first time. I won't posit which one, which area, which resource, but somebody somewhere in one vertical will have started to make some serious progress.
All right, thanks you. Can we get the Slido slide back up? And I've got a few questions, but we still have a few minutes for those that have additional questions, and I will review them and then pick one. And so, in terms of maybe first to Tim, and the question is, are you planning to upgrade the Nova Hopper technology to provide future delivery surfaces on the moon's surface?
Yeah, absolutely. So the Micronova hopper that we're flying on IM-2 was sized to provide 8 kilograms of payload, 25 kilometers of range. However, that's a propulsion sizing activity. So as we get to specific customers who say, well, look, this is exactly what I want to do and how I want to fly, we can upsize or downsize the tank and begin considering refueling technology. So once we demonstrate the basics of the hopper drone activity, customizing that then to be very specific, whether it's as an astronaut's survey assistant or a very low altitude science platform, is something we can specialize into once we've demonstrated the core technology.
Okay. This next question I'll have both for Vera and Masaki. I think it's an interesting question, and your two organizations, well, ISIS, JAXA, and ISRO are with future missions are very interesting. The question is about interoperability. Maybe for you two, what is your vision of interoperability required for cooperation between different parties? And you probably know what I'm talking about in terms of JAXA, ISIS, ISRO cooperation on future missions. So in terms of interoperability between multiple parties, multiple elements, multiple systems, how do you think about that?
You are asking specific to Chandrayaan, LUPEX mission?
No, just generally, and if you want to add
General,
specifics, it's up to you.
Yeah, the one of the thing is interoperability is very important for the infrastructure utilization, particularly, say for example, Moonlight. We have series of satellites. We should utilize that resources. So for which we have to have a communication frequencies which has to be compatible with respect to the rover or landing mission, with respect to orbiting mission. So this is something very important, as well as for the future thing, like we should standardize like what kind of a payloads it can carry, what kind of a rover capacity it can carry, what is the available resources. So which should clearly define it between the agencies, so that this will be like a shuttle standard platform which can deliver the payloads onto the surface or around the moon, things like that.
Yeah, it's a very interesting question because I've been attending bilateral meetings, and at many of them there was a conversation about interoperability, and yeah, because now, Artemis architecture conversation, we have that big picture, and each space agency or whoever is starting to prepare to say that I will provide this, I will make this, then think about, you think about the fitness to the architecture, and then say, I will provide this element in the whole program. But once you say so, we tend to focus on what you're delivering. And maybe end up not talking enough about the interoperability. Then we're good at this, like the collaboration between JAXA and ISRO. When it's a bilateral collaboration, we do talk about interfaces and blah, blah, blah. But when it comes to providing an element in that big program, and who's going to control it, and you know what I mean? Yeah, I think you're in a position to say your opinion about this, I guess.
Interfaces are important. I think, you know, I think in terms of architectures, in terms of the Artemis Accords and having elements together, you know, amateurs talk about propulsion, professionals talk about interfaces, you know, one could say, you know. So I think that's going to be important. And also I think to Tim's point, my perspective would be interfaces that you can repeat and are repeatable, docking standards that are out there, that are known, et cetera. So I think that that's probably some thoughts there. Oh yeah.
Like we have having conversation on LoopX. So I was always wonder that this kind of conversation, can it be applied? You know, can we hope we don't have to repeat this because, you know, no, yeah.
I think of the CubeSat standard. You know, what we see today on the small satellite side was enabled by a standard from a university that other universities could take and build upon, and now they're building 50 kilogram, 100 kilogram satellites, but that standard helped innovate and continue to innovate. Maybe now to Dan, a question is, I thought this was an interesting question in terms of 60 years ago, Surveyor successfully landed on the moon 5 times. Did that experience provide technical insights to the US providers, and is NASA capturing lessons learned from these and other missions for future use?
Yeah, absolutely. We were very grateful, actually, that NASA had set up a no-funds exchange program called Lunar Catalyst back in the day. And that was enormously helpful because we got access then to lots of legacy understanding and data, but then also actual folks that are still working the agency. So combined, it was really helpful for us to be able to at least cross-check what we're doing. You know, we didn't always necessarily go the way that NASA would have gone on a particular solution, but it at least allowed us to round out our thinking and to be able to pressure test, if you will, certain ideas, certain approaches. And so 100%, I think, you know, not only from those missions, but all of the missions, everyone up here and other missions that have happened, we pay close attention. And it's always been, I think, really heartening that obviously there's a certain amount of information that you have to hold proprietary, but at the same time, the community's been generally pretty open about the key lesson learned from each mission, and we've all benefited from those key lessons. And so I think that's what's going to make all of us stronger and better.
Yeah, I'll just add to that. We had a conversation with an engineer from Beersheba, the Israeli lander earlier. There are at least 4 improvements we made on Nova C in its design and development as we watched other people complete their missions. And we went, oh, wow, that got them. Let's change that and modify that right there. And so sometimes it's formal, like the reviews we had with NASA after our missions where we exchanged them. Sometimes just watching someone else make the attempt, and then when the other teams are open and forthright about, well, okay, look, this is what happened. At the minimum, it gives you a chance to go back and look at your design and go, am I susceptible to that? And if the answer is no, good on you. Right? You beat it before it happened. But there were 3 or 4 times, I'm looking at Trent in the back and make sure I've got that right. That I know 2 of them, he and I were sitting in a room together watching someone try to land and went, oh, get the eraser out and just fix that right now. So it definitely builds for a community.
I think this is the reasons I wanted to do this panel, of the moment that just happened, because what you noticed is one lunar lander provider is talking about the lessons learned for another lunar lander provider. So in 2024, this is where we are. This is the future we tried to get to in terms of a lunar ecosystem. And I think you just described such an ecosystem of lessons learned, et cetera. I think we have another series of questions going to the Slim lander, Masaki, on surviving the lunar night, thoughts about that. So I think we had several questions on that. So I'd kind of ask you to talk about that.
Well, I don't think I can answer those questions because we didn't design it, but it happened 3 times. So night survival by the smallest lander on the moon for 3 times. And yeah, we were supposed to be, how do I say it? We're supposed to be like, you know, yay about this, but we just didn't design it. So what can I say? Maybe made in Japan quality. That's all I can say.
Maybe to anyone in the panel about larger lunar landers. You know, as you think about kind of going upscaling at larger capabilities, sample return capabilities, et cetera, how do you think about moving out, expanding your system capabilities? I don't know, to anyone in the audience, yeah, or in the panel, yeah.
Well, we want to. Basic economics, especially for the commercial landers, is with a smaller amount of payload, that's all you can really monetize to pay for your booster cost and your lander cost. However, what you typically find is, we're going from 130 kilograms with Nova C to somewhere north of 1,500 kilograms on our cargo class Nova D. So it's an order of magnitude increase in the payload capacity, but it's not an order of magnitude increase in cost. And so what that allows us to do, and especially in terms of offering more people access to the moon, not only can we take more mass, we can reduce the price for the transportation that we are doing. And it's very much analogous to what you see in the booster industry. That as we got bigger boosters, the price per kilogram came down. So I think moving to the larger landers is essential for us to be able to open up not just more stuff you can take, but to bring the price down so that more people can participate.
Yeah, I'll add, I think it's essential. I mean, ACU pointed out that the HLS program out of NASA, fantastic, but those are very large landers. It's going to take quite a bit of cargo to fill one. And at the same time, too, I think we all have ambitions to have payloads that are larger than maybe some of the scales that we're currently launching at for the landers that are on stage here, being represented on stage. So there's definitely a niche, I think, that need to get to that multi-hundred, at least, kilogram delivery, if not multi-metric ton, because there's going to be a need for things like T-shirts and toothbrushes to Artemis. They're going to need resupply, and you don't necessarily want to human rate every single lander that delivers that kind of cargo. So there's very practical reasons to go to that larger scale, hopefully in the near term.
Let's see, kind of a more market question or demand question. What's a killer app, you think, the question is, killer application that would free lunar lander services from depending upon government funding exclusively? Killer apps, what are your thoughts? Anyone on the panel?
Resources.
Resources, all right. Okay.
Yeah,
one word.
That's an easy one. Certainly there's a variety of different ideas and approaches. I think that's the most obvious one. It's not to say that's the easiest one, though, either.
All right. I will take moderator's prerogative to ask a question I didn't tell you all I'd ask you. So, okay. All right. You're okay with that? Okay.
Go for it.
All right. I magically have $20 million in my pocket. Okay. I'm giving you $20 million to mature a technology immediately. What technology would you immediately apply that for that you're not already funding? So there you go. All of you have to answer this question. So you got 20 million. AC is giving that to you, not NASA, but AC. What are you going to invest that immediately in terms of a single technology advancement for your entire program? Down payment on a technology advancement.
So one is the propulsion technology. For example, we have to increase the specific impulse. Largely, the moon mission is driven by the propellant requirement. So the payload mass at the surface is very low because the large mass is spent in the propellant. So the more the specific impulse is, the better the payload mass. So if we have engines like cryogenic engines or LOX-methane engines, where we have a better ISP than the bipropellant systems. So if we have that, how to manage thermally and how to stay for a longer time, that will be the key. I would go for that.
All right.
I'm going to spend $20 million on valves.
Valves, all right. Okay.
Yeah, I'm right there with you, Dan. I'm going to spend $20 million on the biggest antenna I can get to deploy to bring data down, because the value of the moon is what you bring back. And right now, what we bring back from the moon is data. And we had a lot of help from the internet when we landed that we weren't bringing enough pictures home. More ability to bring that data down. Now, the Moonlight, Near Space Network Services, the constellation is going to help, but I would immediately improve communication technology.
Yeah, Lunar Night Survival Module Next time we design it so that we can survive. Well, seriously, when we talk to our scientists, there are two big science themes we are trying to pursue on the surface of the moon. One is a seismometer, and the other is the radio astronomy on the far side of the moon. And both needs to continue observations for months, like a year or more than a year. Then you have to think about the survival, lunar night survival. So, and the radioactive heating unit is a sensible topic in Japan, but still reasonably, you have to go for it. So yeah, survival module.
And then maybe a final question to the panelists is talking about your experience. You'd mentioned comm and in-space comms, and let's talk about the ground networks, the ground stations that you all kind of had to interact with. We at NASA have the Deep Space Network, and we provide that to our commercial and international partners for certain missions. So can you talk about the ground networks in your missions and thoughts, challenges, observations on the ground networks you had to all employ in different ways? So all of you, I think I'd be interested in that question, yeah.
Well, one thing I would say is the truth of international cooperation is proven when you go to space, because you have to have ground stations around the world. And I can't tell you what a relief it was when you were waiting for acquisition of signal and you would hear Okinawa dish come on and say, I am Houston, I've got connectivity, or our dish in India that we were using. And so all around the world, it really does tie these missions together, because you feel that the team is humans around the planet working together. So I think there's a camaraderie, and it really it changes the way you look at things. I know I haven't had the fortune of going into space, but you hear about the transformative experience of going to space and seeing the world, hearing all the different accents and the different time zones and different music in the background sometimes when people from different dishes were supporting us. That ground network is essential. And we're going to need the DSN, we're going to need commercial dishes, we're going to need dishes from places, especially in the southern hemisphere. We don't have enough dishes in the southern hemisphere. So I really think that is an international effort that ties all of us together when we have to have reliable, continuous comms.
Other thoughts?
Yeah, we're located in an interesting longitude. There aren't that many antennae in the part of the globe that we are situated. So yeah, so we get the request quite often, and that makes us realize, as Tim said, that we are part of the global effort. And yeah, I hope we can maintain our antenna system so that we can live up to the expectation from our partners.
Vera?
We used Chandrayaan-3, our ground station at Bailalu. It's at Bangalore. That is a 34-meter antenna. Yeah. And also we have utilized from JPL 3 stations, Goldstone, Canberra, and Madrid, as well as from ESA 2 stations, Kuru and Gunili. With all that, also we have a visibility gap, I was telling, and these stations are very important. And we are also looking forward for another station which is coming up, geographically separated zone, so that we will have a good coverage. In addition to that, we also have IDRSS satellite which is coming up. That is a relay satellite which will be utilized for our Gaganyaan program. So that also will be used.
Yeah, Dan. Yeah.
I think I would just add that I'm excited for all the investments being made for more dishes and bigger dishes.
Can I ask the organizers to put back the slide of the real pictures of the lunar landers? I mean, our pictures are good, but I think I like that picture better. But yeah, with that, I'd like to thank the audience and everyone for this panel. I would say I'd like you all back next year for my panel, if they allow me, but I don't. I want a new crop of lunar lander countries and companies to be on this panel with me. However, in 2040, I do expect you to be back on the panel with me to talk about your visions and if they came to reality. So
Deal.
All right, deal. All right, with that, let's thank our panelists. And I definitely want a picture with all of you and these real pictures. So thank you.